Okay, our next display technology is DLPs. We typically see these in projectors. There were some TVs that were built doing this, but we typically see it in projectors. So what is a DLP? Um, this is going to involve some microelectronics, which are little mirrors which tilt around, and we'll see that some more. And it's also going to be our first example where colors are not stacked next to each other spatially. They're going to be stacked in time. So it has some fundamentally different property. Okay, here's our little flipping mirrors. I hope this GIF is doing the right thing. And here's a scanning electron microscope looking at this, and some of these got broken off so that you can see the structure underneath. So I have no idea how they build it. I'm not a hardware guy. I can't even imagine building these tiny little structures. But anyway, what you have is you have a chip, which has a bunch of tiny little mirrors on it. And we can flip it to two states. Basically, flip straight and flip to the left. So what are we going to do with this thing? And it can flip fast. These things, so we were talking about displays being 60 hertz. These things flip at like, I don't know, 10,000 hertz. So we can turn them much faster than we can change the rate of information. So an LCD, for instance, if I could change the colors on my LCD in 1 millisecond, that would be amazing. Most cheap LCDs, I want to say 5 millisecond change. For how long does it take to actually change the color at the pixels? And this thing is much faster, order of magnitude faster in terms of how fast it can flip. So what are we going to do? We're going to have a light source. We're going to have some focusing optics. We're going to have a spinning color wheel. And so this color wheel is, when the light hits red, then I only have red light coming through. When the light's on green, there's only green light coming through. And then we're going to bounce off of this grid of little mirrors. And essentially, when the mirrors point one way, the light goes off and just hits a black thing and stops. And when the light goes the other way, when the mirrors flip the other way, the light comes through this lens and comes on our screen. So forget about color for a minute. Just think about black and white. If I flip all the mirrors to shine through, I'm going to get a white picture. If I flip all the mirrors the other way, I'm going to get a black picture. So I basically have control to put black and white pictures on here. So now what if we want to get color or we want to get grayscale values? So, okay, here's our DMD. So if we want to get color, we first deal with our red picture and then with our green picture and then our blue picture, right? Because we keep changing the color of the light coming through. So you could replace this color wheel with some fast LEDs or something like that. When it's hard to get enough light doing it that way. So many of these projectors, have these super hot bulbs. As we move over to LED bulbs, I expect this wheel will change to RGB LEDs here. And we'll just flip those directly instead of spinning this thing. That may have already happened, I'm not sure. So what's going on? Okay, if we want to get magenta, rather than turning on red and blue pixels next to each other, we're flipping on and off these little mirrors. So now this is time, right? So when it's red time, we turn the mirrors on. When it's green time, we turn the mirrors off. When it's blue time, we turn the mirrors back on. So this color, instead of our brain being required and our eye focusing system being required to take tiny little red and blue things and blur them together, now we better flash this stuff fast enough that our brain can't keep up and just thinks it's magenta. So if we're white, we're going to turn on all of these things. If we want a gray value, okay, if we want black, we just don't turn on anything. If we want a gray value, that means less light got here, but it saw all equal amounts in red, green, and blue. So we turn on red for a little while, and then we shut it off, and we just show black for a while. And then we turn on green for a little while, and then we shut it off and show black for a while, and turn on blue for a little while, and shut it off and show black for a while. So there's a lot more flashing of colors going on in a DLP than there is in an LCD, but each pixel is really that color. They're not stacked next to each other. So here's a real color wheel. You can see there's more colors on here, right? So one of the advances is to say, instead of just red, green, blue, maybe we can have some cyan and yellow things on here also, and it will let more light through, because of course red, green, blue is blocking a lot of light. So we can move to a subtractive color space. These are enhancements that I think are not necessary to understand the core differences in this display. But here's a 6-color wheel, right? So if we had a 6-color wheel, we might show instead of just red and green, we also have this yellow time period that we're allowed to use. And because we have a yellow time period, our total fraction of light goes up, and so we can get a brighter display. And white is still going to be the summation of everything, right? And so we can use these combination color spaces. And this has been explored a little bit in terms of how to generate colors. So I guess this additional way to pack the colors is also an interesting thing. Of course, the incoming signal to this projector is always RGB. All of our graphics cards, all of our frame buffers are RGB. I never heard of a graphics card which is storing yellow. This calculation to turn it into this timing with yellow is something the projector is doing. Okay, I think the interesting thing about DLPs is the fact that they're time sequential in terms of the colors instead of spatially. I'm encoding the colors. So this has some implications for fast moving objects. If you take a DLP projector and you stand in front of it and sort of wave your hand around, instead of seeing the interlacing or color fringing that we might see on other displays, we're going to see some kind of weird color rainbows around where the person's moving. And you may have seen this in a classroom with a DLP projector. And I don't have a picture to show that, and I wish I did. If somebody finds one searching around, then post it in the chat or send it to me. I'd love to include a picture of what this kind of color fringing looks like because of the time sequential nature, right? We have to figure out how to flip things off and on. Oh, I should have mentioned also, this is a very simple flipping things off and on. It's kind of crazy to turn on red for a while and then leave it black for a long time because you're more likely to see flicker. So in most real projectors, it would probably turn on red and for a short time be on black, and then turn on red and for a short time be on black. So there'd be some more complicated flipping happening with these things in terms of flipping on and off the things. Also note, because we're going to come back to this concept of dithering later, I can only get black or white. Like I either have full power or no power, and it's only the fraction of time that controls it. If you think about LCDs, I can apply a half voltage to the LCD and half turn the crystal so that only half the light comes through. So I can truly have a gray on a LCD. Well, I can truly have half red on an LCD, right? And then half green and half blue next to it. I can not truly have half red. I can only have full red and no red flipped on and off at different intervals inside this display. Right? We haven't seen any display that can really give us a true 50% gray. It's always mixed out of these other things, which are not really on everywhere if you look at the details.